I'm Bill Lane, instructor at Bellcore Tech. And in this module of the tape series, I'm going to be serving as your instructor as you sort of wander through the information highway or explore the telecommunications network. To make it a little easier, we've broken the network down into 3 manageable components. And those components are customer premises equipment, transmission facilities, and the switching or other switching type facilities. So in this module, we're going to be talking about the customer premises equipment, sometimes known as CPE. Now what CPE is the equipment that the customer owns. And as we know, that can be a variety of pieces of equipment. So let's take a look at them and see exactly what we're dealing with. Customers can have a variety of pieces of equipment attached to the telephone network. They can have plain old telephone service. They can have enhanced telephone service with multi-lines. They can have computers. They can have facsimiles. They can have computer graphic design equipment. All of this equipment has to operate with the network. So it becomes the network's responsibility to be able to communicate and transmit all this information from one customer to the intended customer. So what we're going to do is we're going to talk a little bit about the types of equipment we're going to be seeing and how the computers work, how the telephones work, and how the network transmits these signals. Let's take a moment and look at a videotape on how the telephone works.
It was not until 1875, when Alexander Bell invented the first crude telephone, that society would be able to achieve what is now known as telecommunications, meaning the exchange of information between individuals over long distances. Although the modern telephone set is deceptively simple in appearance and operation, it performs a surprising number of sophisticated functions. To better understand its principle of operation, however, we might do well to first consider the nature of sound. Scientifically, the word sound actually has 2 distinct meanings. A physician, for example, would probably consider sound to be that sensation which is experienced in the human ear. A physicist, on the other hand, would define sound as any atmospheric disturbance, regardless of whether we actually hear it. All of us are familiar with what happens when we toss a small object into a quiet pond. The concentric rings which radiate from the point of impact are one form of wave motion. In this example, water molecules are acting as a carrier of this disturbance. Just as these waves are composed of alternating peaks and valleys, so too sound waves traveling through the atmosphere are composed of alternating compressions and rarefactions. In this case, however, air rather than water is acting as the carrier. Sound, therefore, may also be considered to be a form of wave motion produced by some vibrating object, such as our vocal cords. The telephone, then, is a device which faithfully converts these sound waves into similar electrical waves. As shown on our oscilloscope, it's electric current which acts as the carrier of our words. Obviously, then, what is transmitted through the telephone system is not actually our voice, but an excellent reproduction of our voice. Each telephone is connected to a central office using an access line. Think of an access line as a 2-wire circuit with one of the wires commonly called tip and the other ring. These terms originated during the era of operator switchboards. As you may already know, a central office is the facility which serves many customers in a community and houses the necessary switching and signaling equipment as well as the batteries which power our telephones. In this program, we will primarily be examining the telephone set, its components and functions. Referring to the simplified diagram, These items include the ringer, switch hook, dial, automatic compensation circuit, transmitter, receiver, induction coil, and balancing network. Typically, the ringer is one or two small metal bells, which are repeatedly struck by an even smaller metal clapper. Obviously, the purpose of the ringer is to inform us that a call is coming in. This is possible since the ringer circuit is always connected across the access line, permitting it to operate even when the handset is resting on its cradle or on hook. Notice that while the handset is on hook, the remainder of the telephone circuit is essentially isolated by the open switch hook contacts. The traditional ringer uses a single coil of wire with a laminated steel core and operates on the principle of electromagnetism. Unlike the rest of the telephone set, however, which operates on direct current, the ringer is activated using alternating current from the central office. In other words, alternating current flowing through the coil magnetizes the steel core. Being metal, the clapper is then repeatedly attracted to and repelled by this magnetism, striking the bells in the process. Typically, the ringing voltage is about 90 volts. To avoid a constant ring, however, the alternating current is repeatedly turned on and off to produce a ringing cadence. This is accomplished at the central office using a device called the ringing interrupter. In general, the ringing cycle takes about 4 seconds, 1 second on and 3 seconds off. Next, let's briefly discuss the switch hook, which opens and closes a set of electrical contacts inside the telephone. When the handset is lifted from its cradle, the switch hook contacts close, permitting direct current to flow from the central office through the access line to the telephone set. But when the handset is resting on its cradle, only the ringer is able to operate. We should point out that the simple act of lifting the handset also signals the central office that a call is about to be made. We refer to this as loop signaling. In other words, the electrical loop between the central office and telephone set is complete. Almost instantly, a tone generator sends dial tone through the switch hook and to the receiver, indicating that the central office is in fact ready to receive dialing instructions. Notice that our oscilloscope displays the symmetrical dial tone waveform very nicely. This brings us to our third component, the dial. All of us have probably used both types of dialing. Pulse dialing, which is accomplished with a rotary dial, and dual-tone multi-frequency dialing, which is accomplished using a push-button keypad. In the conventional telephone set, pulse dialing is accomplished using a rotary dial with 10 evenly spaced finger holes. During the time that the dial is returning to its original position, the electrical current supplied to the telephone is repeatedly interrupted by a small cam in the dial mechanism. Each time this occurs, a voltage spike or pulse is transmitted to the central office. 1 pulse is sent for digit 1, 2 pulses for digit 2, up to 10 pulses for digit 0. Because dial pulsing was originally designed to operate the relatively slow electromechanical switching systems, a governor in the dial mechanism limits its return speed to about 10 pulses per second. Unfortunately, when the dial pulses eventually reach the central office, they are no longer symmetrical. During transmission, the added distance of the access line causes them to become rounded or distorted in amplitude. The central office equipment, however, must still be able to detect these as dial pulses. Other types of telephone sets use dual-tone multi-frequency or DTMF dialing to generate and send telephone numbers. DTMF dialing can only be used, however, if the central office is equipped with a DTMF receiver. Telephone sets employing DTMF dialing use a keypad rather than a rotary dial. The keypad generally has 12 keys which represent the digits 1 through 0 and the symbols star and pound. Depressing one of these keys causes an electronic circuit to generate a combination of two tones. There is a low frequency tone for each row and a high frequency tone for each column. For example, pressing key 5 generates a low tone of 770 cycles per second and a high tone of 1,336 cycles per second. By using a 12-button keypad, 12 unique tone combinations may be produced with only 7 frequencies. In addition, DTMF dialing is much faster than pulse dialing. For example, the minimum time required to pulse dial the digit 5 10 times is over 6.5 seconds. Using dual-tone multi-frequency dialing, however, it is mathematically possible to dial the same number in less than 1 second. Let me give it a try. Well, maybe I'm a little slow. The end result of this increased speed, however, is that less central office capital equipment is required for a given number of access lines. This helps reduce the cost of establishing and maintaining a central office. The part of the handset that we speak into is called the transmitter. This only makes sense since it converts speech energy into electrical energy, which can then be transmitted through the distribution system to a distant receiver. The most common telephone transmitter in use today is the carbon transmitter. It consists of 3 major components: a chamber, thousands of carbon granules, and a dome-shaped diaphragm. When the handset is off-hook, these 3 components become part of an electrical circuit which is supplied with direct current from the central office. The diaphragm is a circular piece of metal which is rigid around the edge but flexible near the center. This flexibility permits the diaphragm to be very sensitive to the sound pressures of the spoken word. In fact, it vibrates in exactly the same pattern as these sound waves. Not surprisingly, the movement of the diaphragm simultaneously varies the pressure on the carbon granules. When the diaphragm is pressed toward the carbon, the granules are compressed and the flow of current from the central office is increased. When the diaphragm is relaxed, the carbon also relaxes and the separation between the granules becomes greater. This separation causes a decrease in the flow of current. When we speak, this change in the flow of current occurs hundreds, even thousands of times each second in exactly the same pattern as our speech. It's this change in current which effectively converts acoustical energy into an equivalent electrical signal. The electrical signal is then transmitted through 1 or more central offices to some distant receiver where it is converted back into sound waves. This is the magic of telecommunications. Because customers live at varying distances from the central offices, it would be desirable to have the electrical signals from all telephone sets arrive at the switching equipment with about the same level or volume. To achieve this, our typical telephone set has an automatic compensation circuit. Briefly, this circuit automatically adjusts the current through the transmitter so that speech levels will be relatively constant at the central office, regardless of the distances to individual telephone sets. The telephone receiver is that part of the handset you hold close to your ear. As you suspect, its only function is to convert analog electrical signals into electrical energy. The most common type of receiver used today contains three elementary parts: a permanent magnet, a diaphragm, and an electromagnet. The electromagnet is a circular piece of metal around which is wound hundreds of turns of copper wire. The permanent magnet is positioned so that it constantly attracts and pulls the diaphragm to a slightly biased position. The electromagnet, when energized with electrical current, will then vibrate the diaphragm about this biased position by merely increasing or decreasing the pull already exerted on it. This approach not only increases the amplitude of vibration, it also prevents the diaphragm from vibrating too often, eliminating what's called frequency doubling. Let's illustrate the entire concept. Again, electrical signals enter the receiver by flowing through the wire of the electromagnet. As the electrical current increases and decreases, the electromagnet alternately aids and opposes the permanent magnet, driving the entire structure like a piston. When the diaphragm vibrates, the nearby air molecules are compressed and relaxed. It's this vibrating air which actually recreates the sound waves which were originally directed into the transmitter. There are millions of access lines throughout the distribution network. For economic reasons, these access lines are two-wire circuits. Although the telephone set itself is a two-wire instrument, the handset is a four-wire circuit with two contacts for the transmitter connection and two wires for the receiver connection. This is also illustrated in our diagram. The purpose of the telephone set induction coil is to interface the two-wire circuit with the four-wire circuit, permitting full duplex operation. Full duplex simply means the transmission over the circuit can occur in both directions at the same time. In our telephone set, there is a balancing network which permits a small amount of transmitted signal to be fed to the receiver. This is called side tone. Side tone is the hearing of one's own voice in the receiver while talking into the transmitter. Tests have confirmed that too much side tone encourages callers to lower their voice, while too little side tone causes them to talk too loudly. The purpose of side tone, therefore, is to satisfy the caller that the telephone is indeed working and to control talker volume within predictable limits. At the beginning of this program, we mentioned that the telephone set performs a surprising number of sophisticated functions. Briefly, we have reviewed how a typical telephone can request the use of the telephone switching system by simply lifting the handset, indicate that the switching system is ready for use by receiving a dial tone, generate and send the number of another telephone when the caller rotates a dial or depresses a keypad, indicate the status of a call by receiving tones such as audible ringing or a busy signal, indicate an incoming call by ringing a bell or some other device, convert acoustic energy into analog electrical signals for transmission, and then convert analog electrical signals back into acoustic energy, and signal the system that a call is completed when the handset is placed on hook. The telephone. It's a marvelous invention. I doubt, however, that even Alexander Bell ever dreamed that today there would be close to 182 million telephones nationwide. Telephones which can be linked through over 60 quadrillion possible connections. We call it telecommunications. In biology, it would be called the human nervous system.
So now we have a better idea about how the telephone works. Now that may seem like a slightly archaic device, but that's really what the telephone network has been designed and placed to transmit and receive the signals for. What that means is anything else we add to it must still be conducive to those kinds of transmission characteristics. Well, let's look at some of the other kinds of equipment one might see. Beside a plain old telephone, you might see something we call a key telephone. Now, what is a key telephone? It's a telephone set that has many lines attached to it. Actually, it could be between 2 and 5 or 6. Each line would have a respective key. When that key is depressed, the telephone would be connected to that line. Usually includes a whole button. In addition to that, another voice grade piece of equipment you might see would be a private branch exchange, sometimes referred to as a PBX. That might be a switchboard, is a better known term, where you might find that in an office building, certainly in a hotel, or any large facility that wants to control the transmission. A switchboard provides access for the individual telephone lines within that building, for incoming and outgoing calls, also provides things like voicemail and data transmission. Facsimile equipment would have to go through that. But this is under control of the customer. It acts like a small switch. And as I said, we're probably more known to it as a switchboard. Again, we have to pass voice grade communication. Well, that doesn't seem particularly difficult. And if that was all we had to deal with, that certainly would be the case. But unfortunately, we're not just limited to voice grade transmissions anymore. We have a lot of data equipment out there. Well, what exactly are we talking about with data equipment? Well, you might see things like a computer. Many of us have computers at home. Many of us have computers at work. Computers don't generate a voice signal, a sine wave or an analog type signal, as we'll be talking about later in the series. It generates a series of on and off pulses we call digital pulses. And they operate entirely different in the network than does our voice. To make them operate, we usually add some sort of a conversion device from their digital transmitted signal to an analog signal again to go back and work on our network. These are often called modems, which stand for a modulator-demodulator, or sometimes referred to as a data set. These pieces of equipment, as I said, allow us to use a digital piece of equipment in part of the analog facility in the network. So these are the kinds of things. Now there's a lot of other equipment, but basically it falls within these two categories, voice and non-voice. We complicate that a little bit in the fact that very often we take our data equipment and we connect them together, and we call these networks. Very often they're within a building. You might find them within a college campus or maybe a large medical facility. Certainly large corporations and office buildings tie their computers together in their own internal network. Hence we get the name Local Area Network, or LAN. On a LAN, you will see a series of connection points. These are made to represent an individual computer or PC, as you might call it. And they are connected together very often through a local network. But when you have a multi-facility, for example, let's say a college campus, you might have all the computers in one building tied together and all the computers in another building tied together. Well, perhaps this college has an extension facility way across the town, and they would have computers and they would be tied together. Now what we have is three basically separate networks. It would be much better if they could all be tied together and work together. So somehow we have to take these local area network or LANs and tie them all together so that they could work as if they were all in the same facility. This is what we call LAN interconnection, and it requires, again, the transmission of those signals through our network. Unfortunately, that nice little data set or modem that we put in our personal computer to work on a telecommunications line is no longer going to be adequate to work when you have a local area network. You have so many computers and so many signals that you're just not going to be able to manage it through one little data set. So it's going to become necessary to put in some larger pieces of equipment with greater capacity to transmit this tremendously large increased signal. But again, that's part of what we're going to be talking about as we go through the network. Let's talk a little bit more about this customer and the customer's access to the network. Looking at the network as sort of a large entity. We'll call it just a carrier network, and we'll draw a big box around it or a line around it. If that's our telecommunication network, who are our customers? Who are the people that need to be attached to that network? Well, first of all, we do have the individual customers. Those could be businesses or those could be residences. We often refer to this as the local exchange network, and these, of course, then would be local exchange customers. The carrier portion of it requires us to put more and more of these customers together. So we have individual customers, be them business or be they residents. Well, then who else is left? We often refer to the old long-distance telephone companies as inter-exchange carriers. If we refer to this local network as an exchange, somehow we have to carry our transmission, our signals, our telephone calls, if you will, from one network or one exchange to the next. The way we are set up presently, the same telephone company is very often not allowed to do that. So we have to hand that off to what we often refer to as a long-distance telephone company. More technically, we know those as inter-exchange carriers. So they have to be connected to the network that connects to the customers. All right, then, who else might we run across? Cellular carriers. The same long-distance telephone company you may have for your voice may be an entirely different telephone company than the one that might do a cellular telephone, sometimes even referred to as a wireless telephone or even a mobile telephone. These are, again, service providers for transmission that have to be connected to the customer's part of the network, but they require different kinds of transmission capability. They're not long-distance companies going across the country, but maybe from car phone to house phone, or from pager, or from little handheld cellular phones to a business office. So they're a different type of carrier and they have different characteristics. Additionally, you might find other carriers, sometimes referred to as an enhanced service provider, someone who might provide information such as time of day, weather, sports, stock market quotations. They provide a service. They have to be able to be connected to the customer, and we have to make provisions in the telecommunications network for this all to happen smoothly and seamlessly so that the customers nor the service providers recognize that there is anything going on that's not working properly. So really those are basically the kinds of folks who need to be connected to the telephone network, or more appropriately telecommunications, because we've already seen there's a lot more to it than just a telephone. Now, again, things get a little bit more complex. Back in 1983 and 84, the Bell telephone system was broken up from one large entity to many small entities. And one of the things it did is it separated the local telephone company from the AT&T long-distance telephone company. Now, in order to do that, some dividing lines had to be developed that says up to this point your local telephone company carries your information, and then it has to be handed off to your long-distance or inter-exchange carrier. To formalize this a little bit, we've given it a name, and what they've called it is a LATA. L-A-T-A, LATA. Well, what does LATA stand for? LATA stands for Local Access and Transport Area. So here is how those long-distance customers get access to the local area and transport the customer's signal. Why we've done that? Because the federal government felt that it was necessary to separate the local telephone companies from the inter-exchange or long-distance telephone companies. The rules and regulations that go on about setting LATA boundaries and defining LATAs are quite complex. I'll try and simplify them a little bit for you. Some of the rules that go into doing LATA's development are areas with common interests, both economic and social. So if you had two towns that were very closely allied and maybe dependent upon each other, it would make sense to put them both in the same LATA. LATAs very seldom ever cross boundaries between states unless the government and the courts have given it an official waiver. But ordinarily, it's defined within the state boundaries. It also measures up to some government statistical measurement areas. Now, one of the things we don't want to do is we don't want to confuse a LATA with an area code. I'm sure we're all familiar with dialing outside our own area, and you have to dial that 3-digit area code before the phone number. Well, that's for switching traffic. That's not the same as a LATA. A LATA is a boundary where the government says the local exchange carrier has to hand off to an inter-exchange carrier. So it's a different rationale. They're numbered so that the government and the telephone companies can keep track of them. If you were to look at them on a map, what you might see is an overlay of the United States, and on this overlay you'd see a bunch of lines around different areas, and they would be defined as a LATA, or an area within which a local telephone company can operate. And they vary in size by population and by, as I said, the core of interest of that community. For example, if you were to look at Wyoming, with Wyoming you'd find only one LATA. It's a very large area, but a relatively small population with a lot of common interests because of the state agriculture and businesses, so therefore it has been defined as a single LATA. Moving out to California, California being extremely large, high-density populations with varying interest levels, California's been broken up into 11 LATAs, and they are not area codes. And finally, you might get to some place like Texas, the great state of Texas, very large area, a lot of areas with dense populations, a lot of areas with sparse populations. To accommodate that, Texas has 16 LATAs. And you would find that that would vary from state to state. Many in Illinois and New York, as you might imagine, fewer in Idaho and Washington State. But these, again, are defined areas by the government that says, at this point, the local telephone company has to hand off your business to an inter-exchange carrier or long-distance carrier. So now we have a little bit of better feel for, hopefully, what a LATA is and why, when you want to call maybe the next town or the next state, you've got to have a long-distance carrier when they might both be within the same local telephone company service areas. To make a phone call, as we've talked about, a customer has to dial a number. Okay, that's sort of like an address. If you were going to write someone a letter, you'd have to put a unique address on that envelope, and that address would tell the delivery that it goes only to this location. Fine. The telephone company works in much the same fashion. When you want to call someone, you only want to call one telephone number because you're only interested in passing traffic to one other customer. Well, to do that, we have to give each individual customer or each individual station, as we would call it, a unique number. And that number we refer to as the address. Now, we're all fairly familiar with a 7-digit phone number. The first 3 digits of that would be what we would call an exchange, or at least what we used to call our central office code. And then the last 4 digits would be those 4 numbers that are unique to that telephone. If you work in a corporation that has many telephones, you might be able to call other people in your company with just dialing those last 4 digits. That's because you stay within that central office or within that switchboard. Once you leave that, you have to put those 3 digits on front of it, which become the central office or the exchange code. Now, beyond that, we're also familiar with the fact that we have to call long distance to other areas, so they have their own code. Naturally, they're called area codes. Now, the numbering scheme that we use in the United States is not unique just to the United States. Our numbering plan is part of the North American Numbering Plan. This includes the countries of Canada, Mexico, Bermuda, Puerto Rico, and certain other Caribbean islands. So it's a much larger numbering plan than just the United States. But let's take a look at how this number plan is laid out. You're probably aware that the first 3 digits we dial on a long distance call, we call our area code. The plan calls it the number plan area, or NPA. It consists of 3 digits. The first digit has a limitation of only being 2 through 9. The second digit is only a 0 or a 1, and the third digit can be any number 0 through 9. The second set of numbers we call the central office, or as we used to refer to them, the exchange code. The first digit is 2 through 9, and then the last 2 digits are 0 through 9. And lastly, our station code, or that unique code to the individual telephone or piece of equipment we're dealing with, are all 0 through 9s. Now that provides us with a lot of potential combinations, but there is a problem. And the problem is that we have run out of area codes. Now, we haven't run out of country. What we've run out is being able to divide up the country into unique numbers that will handle all the population in that area. The population growth has contributed greatly to the demand for telephones, and as we said, they each require a unique number, and those numbers of possible combinations have just become exhausted. But population growth is only part of the problem. The population that we do have is demanding more and more services, and they want those services unique. They want them distinguished, and therefore a separate number. For example, we probably all have home telephones and a separate number for an office telephone. We may even have fax machines or printers in our office that have unique numbers. Many people have portable or cellular telephones that they can carry in their pocket or a briefcase. In addition, people also carry pagers. All of these devices include separate numbering. And lastly, and probably the biggest and the fastest growing area right now, is mobile telephones. Those phones that we have either carry on or physically mounted into our automobiles. Again, each one of these devices require a separate and unique and distinct number. This is what's driving the numbering plan to exhaust. Well, what can we do about it? Well, let's go back and look at the numbering plan. If we look at the number plan area, we review the fact that the second digit, the P of the NPA code, has only 2 possible combinations, a 0 or a 1. Now, in the large scheme of a 10 numbering plan sequence, that's not significant, except if we realize that that possible number of combination is already exhausted. Because it has the fewest combinations, it becomes the prime candidate for change. And what we have done is, starting this year, is we've increased that middle digit, the second digit of the numbering plan, from a 0 or 1 to a 0 to 9. That means we have 10 number combination instead of 2. This provides literally hundreds of more area codes that are available for customer growth, both in numbers of customers and demand for services. So this is going to relieve the pressure on the numbering plan, but given the demand for services and the growth of the population, not only in the United States, but in the other countries I mentioned, we don't see this as going to be inexhaustible. It's not going to be too many more years, and we're going to have to grow the numbering plan again. Well, this concludes our module on customer premises equipment. We've talked about the customer's equipment, that being telephones and other voice transmitting devices like PBXs or switchboards. And we've talked about those devices that don't transmit voice but transmit data. devices such as data sets and computers and facsimile machines. We've also talked about how the customers are attached to the network and the other carriers within the network beside the local carrier. We've talked about the LATA, or Local Access and Transport Area, which is the handoff between a local telephone company and a long-distance customer, carrier. And then we've talked about the numbering plan, that scheme or sequencing of numbers that provide each and every piece of equipment with a unique and distinguishable number. In future modules, we'll be talking about how the customer is connected to the network through the distribution portion. We'll be talking about how the network transmits that customer's signal and how the unique codes that the network uses to inform the other elements as to where the phone call is going and how to handle it, the signaling and the protocols and language. And then we'll talk about elements in the network such as switches and other connection devices. Later on, we'll even identify new and emerging or growing architectures and services which are available or becoming available. Thank you for joining me.